So this basic concepts we looked at, and then we looked at the disadvantages of low power factor, and then we looked at the causes of low power factor, different types of loads which induce that low power factor in the circuit. And then we looked at the power factor improvement, the basic concept, and it's basically that because the overall loads are lagging, so we need a leading load or a capacitor type load to be introduced in the system to balance out the lagging load. So, and then we looked at some of the equipment which is used for power factor improvement, like the static capacitor, synchronous condenser, and then the phase advancers and their advantages and disadvantages. So let's continue our discussion ahead, and we will look at some of the analysis related to this in today's class. So some calculations we will look at, which we will be using for our one of the tutorials we will be doing on this same concept. So if you look at this phasor diagram here on the left hand side, the voltage is the reference phasor, same as earlier what we drawn. The current I is lagging at some power factor angle phi 1. And then what we did is that we introduced this capacitor for compensating the lagging load, and the current drawn by the capacitor is this IC. So same as the arrangement which we discussed earlier, that you basically introduced a capacitor in parallel with your actual load. So the current drawn by the capacitor is IC. Net here of IC and I is I dash. So I dash is the vector summation of IC and I. And we see that the overall the net current I dash is lagging, but at a lesser angle, at some power factor angle phi 2. So as we discussed earlier also, in this particular situation also you can see that the active component of I and the active component of I dash is same, because the real power which we are delivering is being unchanged. We are not changing the real power delivered to the circuit. So I cos phi 1 is equal to I dash cos phi 2. That is one thing. Second thing was that if we take the projections on the vertical axis, then we can say that this I dash sine phi 2, or the reactive power now being consumed by the circuit I dash sine phi 2, reactive component of the current, is equal to I sine phi 1, the earlier component of reactive power current, minus your IC, because that is the leading, this was the lagging. So net reactive power component now is I dash sine phi 2, which is expressed as I sine phi 1 minus IC. So from this we can write, if you just transpose this second equation, you can write IC is equal to I sine phi 1 minus I dash sine phi 2. And one more thing we'll do here, because basically we want to find out that what should be the value of the capacitor which we need to introduce so that my power factor improves from phi 1 to phi 2. That is what we want to find out. So ultimately, I mean, just the current through the capacitor is not our interest. Rather, we want the value of the capacitance which will be needed for bringing this change from phi 1 to phi 2. So as we know, for a capacitor, if you look at the circuit discussed earlier also, you have some voltage V appearing across this capacitor. And as you discussed earlier also, that for capacitance and inductance, the same Ohm's law type relationship holds, but instead of resistance, you have the reactance. So you can write V voltage across this capacitor equal to XC, which is the capacitive reactance here, multiplied by the IC, the current through the capacitor. So that is what is here. So V is equal to XC IC, and therefore XC is equal to V by IC. And we know that this XC, or the capacitive reactance, is expressed as 1 by omega C, where omega is 2 pi F, and F is the frequency of the voltage and current in the circuit. So therefore, from this relationship, what we can see is that if you just transpose the quantities one side other, and you can say that the capacitance C is equal to IC by omega V. from this relationship. And that is what is given here. Capacitance is equal to IC by omega V, and then you substitute the value of IC here and you get the value of capacitance which would be needed for bringing this change of power factor from power factor angle phi 1 to phi 2. So this is the expression in terms of the capacitance. And equivalently we can do this in terms of the powers also, because so this is the expression in terms of the current rating, but maybe many times the current rating the current reading is not really readily available, because if you look at any practical consumer premises, we don't have ammeters installed, we have the energy meters installed which measure the power consumption. So that's why the equivalent thing in terms of the power also has been done here on the right hand side, if you see. So here in the right hand side, as you see, there are two power triangles. The first power triangle, the base is common for both, because as we said, we are not changing the real power demand. So whatever is the real power demand of the circuit, that remains unchanged. Therefore, the base of the triangle OB is same. But what is changing is that we want to change the reactive power demand. So initially, the circuit was operating as per the triangle OAB, this bigger triangle AB. And in this, OB is the real power demand, AB is the reactive power demand, and the net of the two, that is OA, is the apparent power. So that's why it is indicated as kVA1 and this is kVAR1. And then what we are doing is that we are introducing again some capacitive load here to improve the power factor. That means to bring down the reactive power demand of the circuit. So by introduction of the capacitor, now this point A is shifting to point C. So in the second condition, with the compensating capacitor in place, the operating power triangle for this circuit will be OBC. Okay. And now the reactive power demand is this BC, which is kVAR2, and the apparent power overall is OC, which is kVA2. So that is what is this figure is about. So let's look at it, the expression for this in terms of kVA1, kVA2, and the kW and kVAR2 and kVAR1. If I want to improve from phi 1 to phi 2, what will be the value of capacitor which would be needed? So as it says here, leading kVAR is supplied by power factor correction. So this extra leading kVAR, that means your difference between kVAR1 and kVAR2, that is supplied by the power factor correction equipment. And that is in this figure, as we can see, this is given by the section AC, and that is what is supplied by the power factor correction equipment. So this AC, as we can see, is equal to AB minus BC. AB is kVAR1, BC is kVAR2, so kVAR1 minus kVAR2. And now we can express both of these in terms of the your real power demand or the side OB. So if you just apply simple trigonometry, you can see that tan phi 1 is your AB by OB and tan phi 2 is BC by OB. So therefore, we can write AB as OB tan phi 1 and BC as OB tan phi 2. So the net kVAR which would be required by power factor correction equipment can be written as OB outside common and tan phi 1 tan phi 2. Or alternatively, we can write it as the kilowatt rating of the circuit or the power consumed in kilowatts multiplied by tan phi 1 minus tan phi 2. And this is the reactive power which is being supplied by the capacitor. And again, same thing. Now the reactive power, I mean any power per se, is basically the voltage into current, and because the capacitor has this voltage and current at 90 degree to each other, that's why this entire thing, this quantity is a reactive power. So therefore, this reactive power which is being supplied by the capacitor, we can write it equivalently as V into IC, voltage across the capacitor multiplied by the current through the capacitor. This voltage multiplied by the current. And basically depending upon the angle between V and IC, this power can have different quality. It can be completely purely real power. If this voltage and current is across a resistor, then it will be a real power. If it is a mixed load, combination of R, L or C, then it will have some particular power factor angle different from 0 and 90, somewhere in between. And if in this case, like we have completely across a capacitor, and so the voltage and current will have a 90-degree temperature, and therefore this is entirely reactive power. And therefore from here we can write it as, just transposing it to the other side, IC equal to kW into tan phi 1 minus tan phi 2 divided by V. And same applying this equation, capacitor value is equal to IC by omega V. We can write capacitor rating here as kW into tan phi 1 minus tan phi 2 divided by omega V squared. And here if you see, all these quantities are easily measured. kW is from your energy meter reading, you can get that. Phi 1 was the initial power factor. So obviously if you are improving power factor, means you have a power factor meter at the consumer center. So that was the initial power factor angle, phi 1, and phi 2 is the new power factor angle. Omega is nothing but 2 pi f, and V is the rated voltage of the circuit. So this would be more practical to find out the value of capacitor needed for improving from power factor angle phi 1 to phi 2. Any questions on this? Any confusion anyone is having? Please feel free to ask. Okay, so I hope it's clear to all. So let's move ahead. Just continuing the discussion earlier, what we had regarding the the advantages and disadvantages of different types of phase power factor correction equipment, and what are the problems, why this, what are the disadvantages of low power factor. Just a corollary of that basically is that what are the benefits of power factor improvement. We do the power factor improvement, and this is coming straight away from that disadvantages of low power factor. But still, for sake of completion, we are mentioning it separately. So benefits of power factor improvement for different entities, different can be there. So if you look at the consumer end, this here, when we are talking about the consumer, please remember that this is for the bigger consumers, the industrial consumers typically, who have to pay not only just for the energy consumed, but also the apparent power and the maximum demand in the kVA terms. So this is for consumers who has to pay electricity charges for his maximum demand in kVA plus the units consumed, kilowatt hour. Okay, so that is the context of consumers. This will not be applicable for small residential consumers or small commercial consumers who only have to pay in terms of the units consumed. For them, power factor correction doesn't have any benefit per se, until and unless there is a penalty or something of that sort. But for the bigger consumers, the industrial consumers or large commercial establishments or even institutional establishment like IITs and all, whoever is having a contract demand with the utility, that they will have their maximum demand also monitored in terms of kVA along with the units consumed. For them, there is definitely a benefit. So because the idea is that there is this is known as the contract demand. So there is a contract demand which this user or consumer will enter into agreement with the utility which is supplying power, that their power demand will never exceed whatever is the upper limit of they have decided upon in terms of kVA. So, and also the many times as part of that agreement, there are benefits also, that if you manage to have a lower kVA, then you get a benefit. Sometimes it is in terms of the power factor also, that if you maintain a power factor in this particular range, then you get a surplus or a discount on electricity bill, something like that. So for those consumers, as we can see, if the consumer improves the power factor, there is a reduction in his maximum kVA demand, because maximum kVA is nothing but the kilowatt divided by the power factor angle of the cos phi, power factor of the circuit. So if we improve the cos phi for the same peak demand, peak real power demand, the maximum kVA goes down. So that is the advantage there. For generating station, there is also advantage. So as it says here, the generators in a power station are rated in kVA, but the useful output depends on kilowatt output. So as we have discussed also earlier, that the generating equipment is always rated in kVA or MVA, because when you are generating, there is no distinction between real and reactive power. The distinction comes from the consumer and from the, depending upon the type of loads you have in the system. So you're generating in kVA, but usually, I mean, the monetary benefit or the commercial benefit is only for the number of units which is actually produced, that is the kilowatt output. So therefore, it's always advantageous that if you can improve the power factor, then what will happen is that it is greater the power factor of the generating station, higher is the kilowatt hour it delivers to the system. So for the same kVA rating, if I improve my power factor cos phi, make it higher, then your number of units delivered will be higher in terms of kilowatt hours. So that is the advantage for generating station. Now we'll look at two particular cases, two special cases you can say, related to the analysis of power factor improvement. Because one question can be there that to what extent should we improve this power factor? That there is some phi1 which is existing in the system. Let's say this phi1 is whatever, let's say it is 45 degrees, which is not really a good power factor angle because cos phi will be 0.070 or something, 170% power factor, which would be not really good. So how much should we improve? Should we take the power factor to 80%, 90%, 95%, or just 100%? That is one question which will definitely need to be answered, because if you want to, because the sizing of the capacitor which would be needed would depend upon how much improvement you need, what is the final value of phi2 you need. So theoretically speaking, we would say that okay, if we get 100% power factor, that is best. But practically speaking, we should know that there is a cost which is involved. So improving from 70 to 80 will have some cost. If you improve from 70 to 90, then you will need a bigger sized capacitor. The cost would be different. And if you improve further, then accordingly the cost goes up. So basically, this needs to be decided based upon the economics of the particular situation in terms of what is the rate of power consumption at which the electric utility is charging you, what is the rate at which the capacitors are available. So basically it will be an economic decision so that you can maximize the benefit out of the power factor improvement. So let's look at this from, so this is from the consumer's point of view. As we said, there are two point of views from which you can look at this problem. One is from the consumer's point of view, that they want to reduce their maximum demand so that they have to pay less charges for the demand. And another is from the generating station's point of view, that so that they can produce more useful power output, the real power output for the same kVA rating. So this most economical power factor, what we are doing or talking about, or we're going to discuss now, is again, it's only from the, basically from the consumer's point of view. So with that background, let's look at this analysis for the most economical power factor. So as we understand, if a consumer improves the power factor, there is reduction in his maximum kVA. As we discussed, if you improve the power factor, if you make the cos phi higher, then the maximum kVA which will be demanded from the utility by the consumer would be lesser. And this leads to some annual saving over the maximum demand charges. So usually how it will happen is that you will have an upper limit. It should not breach above that. Above that there will be severe penalty. And within that limit also, usually there are some maximum demand charges. So how much was your kVA demand in a particular billing cycle? Maximum kVA demand. Based on that, there is a particular bill which will be generated. So if we can manage this maximum demand and keep it to a lower value, then we get an advantage over that. I mean the economical benefit in terms of the reduction in the electricity bill. But as we said, there is a trade-off. One is that you are saving on that, but to have that saving, you need some power factor improvement equipment, which will need some capital investment. So let's say you are having a capacitor bank or a phase advancer or this synchronous condenser, any of these options or any other of the modern power electronic options also. Then also, I mean, in either case, whatever is the equipment you are using, there will be some capital investment which will be involved. And for the practically also, if you look at it, usually how this capital investment is made is that usually it is taken as a, on a loan basis. So there is some interest which you'll have to keep on paying. So it will be, this capital investment can be equivalently converted into recurring expenditure in form of annual interest and depreciation on the power factor correction equipment. So whatever is the upfront cost of the equipment. Now, if you are taking that on a loan, then you have to repay it back in terms of the interest you pay again over the years, and there will be some depreciation. So depreciation is also very standard term. Most of you must definitely be knowing about this. So any industrial equipment which is purchased, there is something known as the depreciation accounting which is done, that what will be the useful life of the particular equipment and how the value will depreciate, and so that you can manage, you can create, if you pool that amount, the depreciation amount, in a particular separate fund, then by the end of the life of that particular equipment, you will have a ready fund for replacing that equipment with a new one. So that is how it is. I mean, it's not really necessary that you maintain a separate one, but that is how it is accounted for, that there is some depreciation in the price of the equipment in terms of the capital investment. So these two will be the expenditures, the annual interest and the depreciation. So as we can understand, the net annual saving would be the gross saving by cutting down on your maximum kVA demand minus the expenditure, the recurring expenditure in terms of the annual loan repayment and depreciation. So the net annual saving would be the of first minus second. Then the value to which the power factor should be improved so as to have maximum net annual saving is known as the most economical power factor. So we'll do the analysis for this. Is that what should be the power factor to which we should improve so that this net annual saving is maximized, because that is what is going to make economic sense. So the net annual saving is what we want to maximize, and that power factor at which value this net annual saving is getting maximized, that is what is defined as the most economical power factor. So with that background, let's look at the analysis. So let's consider a consumer who is having a peak load of P kilowatt. So the real power demand, peak power demand, is P kilowatt at some power factor of cos phi 1. And the electricity utility, the electric utility in that region, whoever is the distribution company which is supplying to that consumer, they are charging this consumer at rupees X per kVA of maximum demand per annum. Okay. So this is a demand charge, not the energy charge. So rupees X per kVA of maximum demand per annum. So that is the expenditure side. And let's say, the other side, if you want to invest in the power factor correction equipment, then let's say the consumer improves the power factor to cos phi 2. So that was the initial was cos phi 1, which was having a lower value, and now you improved it to cos phi 2 by installing some power factor correction equipment. And the expenditure incurred on the power factor correction equipment is, let's say we are denoting that as rupees Y per kVAR per annum. Okay. So the expenditure on the power factor correction equipment is rupees Y per kVAR. So this is in terms of how much is the reactive power output of the equipment per annum. Per annum, because we are taking the recurring expenditure. So now again we can make this type of a power triangle as we discussed earlier. Phi 1 was the initial power factor, and now you are improving it to phi 2. So with the initial power factor phi 1, the reactive power demand was kVAR1 and the apparent power was kVA1. With the new power factor angle phi 2, your reactive power demand drops to kVAR2 and the power factor angle improves to phi 2. And the real power remains same throughout the power P. So again, applying simple trigonometry, we can see that this kVA1 is nothing but your P by cos phi 1. So cos phi 1 is your P by kVA1. So kVA1 is P by cos phi 1, or we can write that as P sec phi 1. And same way, your kVA2 is this, the hypotenuse of the smaller triangle, that means the side OC, not mentioned here. So that is kVA2. So this OC from the triangle OC, we can write OC or kVA2 as P by cos phi 2, or equivalently as P sec phi 2. So annual saving, now we are reducing our maximum kVA demand from P sec phi 1 to P sec phi 2, and the charges are, as it says, rupees X per kVA of maximum demand per annum. So the annual saving by improving this maximum demand or reducing this maximum demand will be X times kVA1 minus kVA2, or we can write that substituting these values here, we can write it as XP sec 51 minus sec 52. So that is my annual saving. This is the equation 1. Now let's look at the other side in terms of the investment needed for your power factor correction equipment. So the reactive power with power factor angle of at cos power factor equal to cos phi 1 in the bigger triangle, we can see that we can write this kVAR1 as P tan phi 1, and when you improved it to power factor angle phi 2, then you can write in the smaller triangle OAC, you can write kVAR2 as P tan phi 2. So the leading kVAR which is supplied by the power factor correction equipment is the difference of the two, P tan phi 1 minus P tan phi 2. So earlier the reactive power demand was higher, P tan phi 1. Now the reactive power demand of the circuit is lower, P tan phi 2. And the difference of the two is what is being supplied by the power factor correction equipment. So kVAR supplied by power factor correction equipment is this value, P tan phi 1 minus tan phi 2. And same way here, as we said, expenditure incurred on power factor correction equipment, we express that as rupees Y per kVAR per annum. So the annual cost of power factor correction equipment will be nothing but this kVAR saving or the kVAR supplied by the power factor correction equipment multiplied by this value Y. So it will be rupees PY tan phi 1 minus tan phi 2 per annum. Okay, so that is also the annual cost. You have annual saving and annual cost. Equation 2. So as we can, and by the way, just for your reference, suppose, how will you estimate this value Y? Because the value X might be given directly, that this is the maximum demand charges of the utility. So X might be given directly, but Y might not be given directly always, because it might be just given as the cost of the power factor correction equipment might be expressed just as the total capital cost. So if it is expressed in that form, that you just have the total capital cost, then you need to convert it into annualized capital cost. And this Y is nothing but the annualized capital cost per kVAR. So as you can probably, you might have studied hopefully this formula of in terms of the discount rate at some particular place. If you have studied, you might recall that if the overall capital cost per kVAR is this CC per kVAR, then if I want to convert it into the annualized cost, then I need two things. One is that what is the useful life of the equipment in terms of number of years, and D is the discount rate. So usually there is a discount rate because, as you understand, there is a time value of money. So the money which is like, let's say there is 100 rupees at present date, 1 year down the line, that would be the value of that same 100 rupee note would be lesser. 2 years down the line it will be further lesser, because there is an inflation in the economy, and due to which the actual value of money goes on depreciating over the years. So that is what is this discount rate can be taken. Now this discount rate, there is no standard value that you have to take this only. It basically depends upon how much is the inflation in the economy, what is the benefit or interest which you are getting, or the return you are getting on the competing investment. So let's say if someone is having other investment option possible where they can get a 10% rate of return, so they might put a discount rate somewhat higher than 10% as 12%. Suppose all the other investment options are giving just a return rate of 7% maximum, then you might take a discount rate of 8%, let's say, slightly on the higher side. Or suppose let's say that some of the other investment options, the maximum available return rate from other investment options, let's say 15%, then we might take a discount rate of slightly higher than 15% for this case. So it will depend upon basically that if you have some amount of money, then how much return can this money fetch given the present economic situation. And so depending upon that, because this is basically about economic choice, whether I want to invest my money in this power factor correction equipment, or I want to invest the same money in some other competing investment option, because it's basically economic decision. I'm interested about the rate of return. So depending upon those, so this will be a subjective factor, what value of D you should choose. That will be a subjective thing depending upon the prevailing economic condition, what is the inflation rate, what is the competing investment option, what rate of return they are giving. So based on that, this value of D can be chosen. And if you put that value of D in decimal terms here, so if you, let's say you chose D as 10%, so you put D as 0.1, N is the number of years of useful life of this equipment. Let's say you expect this equipment to last for 15 years, so N becomes 15, D becomes 0.1, and then whatever is the capital cost, you substitute that here. So by solving this expression, you get the annualized capital cost or the value of Y. So once you get that, now the net annual saving S is nothing but equation 1 minus equation 2. The annual saving minus the annual cost. So it will be XP sec phi 1 minus sec phi 2, which was equation 1, minus YP tan phi 1 minus tan phi 2, equation 2. And as we know, for maximum saving, we want to, we will have to take the derivative of this, equate it to 0, and the derivative will be taken with respect to the variable phi 2, because that is what is the thing under consideration, right? What should be the value of phi 2 to which we should improve the power factor. So therefore, we have taken this ds by d phi 2, equating it to 0. We want to get the maximum saving. And if you solve it out, just take the derivative with respect to phi 2, you will get this expression. And solving this, what you will get is that sine phi 2 is equal to y by x. So if you just take the derivative and simplify it, you will get this expression of sine phi 2 is equal to y by x. And as we know, the power factor is cos phi 2. So the most economical power factor, MEPF, or cos phi 2, can be expressed as under root of 1 minus. And the interesting thing about this, as you see, is that this most economical power factor depends on relative costs of supply and power factor correction equipment, but is independent of the original power factor. So because the only things involved are Y and X. So it will depend upon what is the maximum demand charges in the charge by the utility and what is the capital investment, annualized capital cost of the power factor correction equipment. But it doesn't depend on the original power factor. So whether your original power factor was 70% or 80% or whatever value, irrespective of that, to what level you should improve will depend upon these two factors. Any questions or confusion or anything to ask or share on this?
Hello, sir. Anvesh, sir.
Yes, Anvesh, go ahead.
Sir, when you are taking the active power, we are calculating the annual saving, and for getting the correction of equipment, we are taking the reactive power. So how we know that, sir, about the reactive power? Active power, I understand that we are taking the annual saving. But,
your question is not clear to me. Can you repeat it again?
So in first case, we are taking annual saving for active power.
Not active power. It is for apparent power. It is not for active power.
Apparent power. Okay, sir. And second case, we are taking annual cost of correction for reactive power. So how we know that, sir? I didn't get that.
See, what we are saying is that your the utility, the electric utility will be charging you in terms of your maximum demand, the apparent power, the kVA rating. Okay. So now what we want is that we want to, if we can reduce this kVA, then we can save on the charge which we have to pay for the maximum demand. Now how to reduce this charge? Only two options are there, because kVA is composed of the real power and the reactive power. So one is that either you reduce the real power or you reduce the reactive power. So typically real power also might be improved. That is also another issue, that if you can improve in this, if you can put some more energy efficient devices, you can improve upon the real power also. But right now that is not the scope of our discussion. So that is also one option available. Into that domain now, we are saying that, okay, let's say your real power demand remains the same. Then what can we do to improve the apparent power is that we can cut down on the reactive power demand. Because as we have discussed, this reactive power is not actually being consumed anywhere. It is not producing any useful work output. It is just circulating in the circuit and consuming some of your current carrying capacity. So this you can, say that it's a low-hanging fruit, because there is no real work output given by this reactive power. So, and even if you want to improve further, you can also go for energy efficiency type of replacements on your equipments, and then you can cut down on the real power also. But that is not what we are discussing here. So keeping the real power same, what we can do is that we can cut down on the reactive power. And if we cut down on the reactive power, then we achieve a saving in the apparent power. So that is the first part. That because the utility will be charging you based on your maximum demand, the kVA demand. They are not charging you based on the kVAR demand. So the kVA demand is what they will be monitoring. So that's why the first part is expressed in terms of the kVA. But ultimately, if you see, it is final expression is in terms of rupees or the monetary amount. Because this kVA 1 minus kVA 2 is what is the active or the apparent power saving. But once you multiply it with x, x is nothing but rupees x per kVA. So this becomes the total monetary value which you are saving. And how we achieved this saving is by cutting down on the reactive power demand. So that's why what we did here is that first we estimated how much is the reduction we need in the reactive power demand. That is P tan phi 1 minus tan phi 2. And again, what this will have the implication in terms of the monetary value, that is what we calculated. So depending upon, because this improvement will be achieved by some power factor correction equipment, so depending upon its cost, you got the investment in terms of the reduction for reactive power. So that's why this expression also becomes in terms of the monetary value or in units of currency or rupees. So therefore, what we are doing, we are not comparing, we are not in this expression, we are not subtracting the active or the apparent power from the reactive power. Rather, it's just the monetary units. So XP sec phi 1 minus sec phi 2 is also money value, rupees, and YP tan phi 1 minus tan phi 2 is also a monetary value. So that is how you're getting the saving in terms of the rupees. That is what we are minimizing. Does that answer your question?
Yes, sir. Got it, sir. And sir, one more thing that if, like in power, when you're reducing the apparent that annual correction equipment, so we can use the material type. We can improve the material quality to reduce the costs. Is it like that?
See, that's what. See, there are two options only. If you want to improve the apparent power, either you cut down on the real power or you cut down on the reactive power. So reactive power we have discussed. It can be done through power factor correction, and real power can also be cut down by having more energy efficient devices in your system. So like one common example which I always give and very common is like replacing your incandescent bulb by a tube light and then by CFL and then by LED. So progressively the power demand is going down for the same illuminations. So that is another aspect of it, and that I think probably those who have taken that AHN-514 that course on energy conservation and management, that will be coming in that domain. That that is also a standard way, is that you cut down on your real power demand by having more energy efficient devices. So that is also a valid option and might be used and is definitely a recommended option. But in this course right now, we are just discussing about the power factor correction. That's why we are not going in that way. But that option is there.
Yes, sir. Got it, sir. Thank you, sir.
And anyone else?
Sir, Souvik here. Am I audible?
Yes, sir.
Sir, these consumers are basically 33 kV and 11 kV consumers. Correct, sir? Individual.
What's the word you use? 33 kV and 11 kV. Before that, what did you say? Or these?
These consumers are
consumers.
Yes, consumers. Consumers are 33 kV, 11 kV consumers.
Mostly, yes, yeah. And I mean, it depends upon the regulations of the particular electricity regulatory commission. So definitely for 11 kV and higher consumers, this will be the case. One thing which we need to make sure is that for the 415 volt three-phase consumer, they might also be coming in the purview of maximum demand monitoring zone, or might not be coming depending upon the regulations from state to state. So that is one gray zone, but definitely 11 kV and above will be coming in this.
So in residential distribution system, I think the state utility will be doing these things, this cost saving and all.
Right. Right. They are expected to do so, right? Okay. Anything else? Okay, so let's, one last thing is remaining here, hopefully we can finish in 5-7 minutes, is that now this was on the consumer's end and his choice of most economical power factor and what will be the things it will be depending upon. Now let's look at the similar decision at the generating station, because as I said, we can look at this problem from the two aspects. One was from the consumer side, another is from the generating station. So similar, analysis, we can look at the generating station, whether they should invest in power factor correction equipment or not, how to take that decision. So this analysis is about the generating station. So let's suppose that there is a power station and it is required to deliver more kilowatts to meet the increase in power demand. Okay, so there was some initial real power demand which was there in the region in which they were operating. They were delivering a particular number of units. Now it is saying that the demand has increased, the real power demand has increased. So how can this generating station meet that extra real power demand? So again, there are two options. One is that you increase the kVA capacity of the generating station at the same power factor. So the initial power factor, let's say, is cos phi 1, and you let it be at that value only, and you increase the overall kVA of the kVA rating of your generating station. But as you can understand, that would be a major investment, because your entire generator and all the other utilities, whatever is the generating station, the generator, the transformer, the turbine, everything is rated for a particular kVA output. So that would be really a major investment. Another option which might be interesting to look at is the improving the power factor of the generating station from cos phi 1 to cos phi 2. Though there might not be very big room for this, because as we discussed earlier, that the generating stations are always having a reasonably good power factor, 0.8 to 0.9. So there might not be a big room for improvement, but if there is a small increase, incremental increase in the power demand, so for some small margin, this option can be explored. If there is a major improvement, major increase in the load demand, then this second option won't work definitely. Then kVA capacity will have to be increased. But for minor increments in the real power demand, this second option might be very interesting and viable. Is that we improve the power factor from phi 1 to phi 2 and keeping the same kVA capacity. So let's do the economic comparison for this also. So suppose your generating station is generating S kVA at some cos phi 1 power factor. So let's look at this here. Now this is the diagram is slightly more complicated as compared to the earlier ones. So here what you see is that initially it is operating as per this power triangle OAB. So OB was the your kVA 1 or the rating of the generating equipment, and it was operating at this power factor angle phi 1. Now what we are saying is that there are two options. Now one is that you keep the kVA rating same and you improve the power factor. So that is what is shown here as this arc going here. So with the same OB, you improve the power factor from phi 1 to phi 2. So basically your OB is equal to OE. It's like an arc with the same radius. So if you shift this vector OB from OB to OE going along this arc, then that is the option when you are having the same kVA capacity, but your power factor is improved. And another option is that and then with that same thing, now you can supply the demand OC. So that AC is the increment in the real power demand. So initially the real power demand was OA. Now the real power demand has increased to OC. So there are two ways of satisfying this demand. One is that you keep OB, the kVA rating same, and you shift this vector from OB to OE by improving your power factor angle from phi 1 to phi 2. Another option is that you put investment in the kVA capacity, and then you keep phi 1 same, but you increase OB to OD. So this BD is the extra kVA capacity which you are installing. So that is the other option, extending this OB to OD with the same power factor angle. Then also you can satisfy the real power demand of OC. So those are the two options. Whether we should go from the operating point B should shift to E, or it should shift. Okay, those are the two options. And how to make the decision? Let's look at the constraints here. So the increase in kVA capacity, one option is that we are increasing the kVA capacity from B to D. So BD is the increase in kVA capacity, and this BD we can write it. If you just do the simple trigonometry, this phi 1, this angle is also phi 1. So this is expressed as BF by cos phi 1. BF is nothing but same as AC, or AC can be expressed as OC minus OA. So you can write it in this form, and OC you can write as OE cos phi 2 from this OEC triangle, and OA you can write as OB cos phi 1 from the triangle OAB. So ultimately it becomes this, and because as we said OE and OB are same, so you can take it out as common, and this is nothing but the initial power, the kVA rating of the linear generating station, that is S. So it becomes S times cos phi 2 minus cos phi 1 divided by cos phi 1. This is the increase in kVA capacity needed. And if X is the annual cost per kVA, so the investment again, what is the extra investment capacity, that will come at some cost, and if you take the annualized capital cost, that is the value of X. So X is the annual cost per kVA. Then the extra annual cost due to increase in kVA capacity would be this. So this is the increase in kVA capacity multiplied by the factor rupees X per kVA. This is the monetary value investment needed, XS into cos phi 2 minus cos phi 1 divided by cos phi 1. So that is one option. Second option is that we don't increase the kVA capacity, rather we add the power factor correction equipment. So in this case, as you can see, what will happen here is that because you have just shifted from OB to OE, so now you can supply that extra demand, or OC can be satisfied, but this particular gap ED has to be supplied by your power factor correction equipment, because you improved from phi 1 to phi 2. So ED is what will be supplied by your power factor correction equipment. Therefore, leading kVAR taken by the power factor correction equipment is ED, and this ED now we can write as your CD minus CE. Again, doing simple trigonometry here, you can change it, and because of lack of time, I'll go quickly to the result. So you can look at the analysis and share the notes. So you get that this will be your kVAR needed for saving, in terms of the power factor correction equipment. This should be the kVAR rating of your power factor correction equipment, S times tan phi 1 cos phi 2 minus sin phi 2. And if Y is the annual cost, again same thing. For again we are talking in terms of the annualized capital cost per kVAR of the power factor correction equipment. Then this converts into a monetary value of YS tan phi 1 cos phi 2 minus sin phi 2. Now there can be different cases. So idea is that the power factor correction equipment will be cheaper if your this cost YS tan phi 1 cos phi 2 minus sin phi 2, which is the your investment, annualized investment for power factor correction equipment, if this is less than the first option, which is the cost of expanding the capacity. So if the second is less than first, then your power factor correction equipment is more viable. So let's look at the limiting value. So maximum annual cost per kVAR of the power factor correction equipment, that would justify the installation. Because if the capital cost of the kVAR equipment, of the power factor correction equipment, if that cost goes on increasing, at some point it will become unviable. So what is the maximum annual cost which can justify the installation of the power factor correction equipment? That will occur when this equation, instead of less than, this becomes equal to. So if you equate the two and you solve for it, then you can get this expression, is that if your annualized capital cost of power factor correction equipment Y is equal to this value, where X is the annualized capital cost of capacity expansion, kVA capacity expansion, multiplied by this factor. So if your power factor correction equipment cost then this value, or maximum up to this value, then it is advisable to go for power factor correction equipment at the generating station. And in case your power factor correction equipment is more expensive, the actual value is greater than this Y, then it is not advisable to go for power factor correction. Rather, one should go for kVA capacity expansion. So I'll share this notes. You can just look at the analysis, but that is the idea behind this. So any questions quickly, because time is over, but any question anyone having? One quick question you can take. Okay, so then we'll stop here, and tomorrow in tomorrow's class we'll do the numerical practice.